All right, welcome everybody. Today we're going to talk about lesson number 91. This is section 12.2, techniques for evaluating limits, and this is just day one. We'll spend several days on this section. This section focuses on all the important algebraic techniques, and again, I can't stress how important those are for next year. Your ability to, get familiar with these techniques now is just going to be really helpful next year to make a good first impression in your calc class, to kind of start off on the right foot. If it's a review next year, as opposed to seeing it for the first time, I think you're just going to be starting off at a great spot. Homework number 91 is listed there, 1 to 21 odd, skip number 11, and then number 24. Please make sure that for 1 and 3, you know that the second part is just asking you to simplify. So first, just kind of a brief reminder of yesterday's lesson. So a brief reminder of limits that do not exist based on the graph. So this first example here, of course, the reason why the limit does not exist at 0 would be because of the fact that this is an oscillating function. Remember, an oscillating function jumps back and forth between only a couple of values. So there would be no limit at 0 because of the fact that it's jumping up and down. This example over here, the reason why the limit at 0 would not exist is because if you compare the left-handed approach with the right-handed approach, they are, of course, not going to the same place. And remember that the left-handed approach is denoted by that little subtraction sign up in the superscript, where a right-hand approach is denoted by a little positive sign there. Remember, you can, in fact, find just one-sided limits at a time, but if they were to ask you for the full limit at 0, that's why it would be does not exist. This example here, at a value of 5, we would say that the limit does not exist because the left-handed approach is going all the way up to infinity, where the right-handed approach is going down to negative infinity. So again, the limit does not exist because the two sides are not going to the same spot. A little bit of a different explanation why the limit does not exist here in the fourth example. It's because that even though these values are approaching the same asymptote, because the values are getting bigger and bigger and bigger, we call that being unbounded. We're going to say for now that the limit does not exist. Again, a special note for these two examples, once we start talking about limits at infinity later in the chapter, we're going to have to revise that. But for now, as far as we're concerned, these are all the different ways for which a limit might not exist. So then another review of what we ended yesterday's lesson with, all the different properties of limits and using the process called direct substitution. Direct substitution means you basically take whatever the C value is, you try to plug it into your function. As long as you are able to find an answer, congratulations, that's the limit. And direct substitution is the dream. If every single problem was able to just plug in the C value and give you an answer, that would be great. Spoiler alert, that's not going to be the case. But direct substitution is always going to be your first line of defense in the limit war. You're always going to try that first. So a reminder of some of the basic limit rules here. If you're trying to find the limit of a constant, obviously there's nowhere to plug in a variable, so you simply get that constant. If you are trying to find the limit of just an x, you would plug in whatever that functional value is, and that would be your limit. If you have something with an exponent, or if you have something with a square root, as long as you are able to actually plug in that C value, you can get an answer. Of course, anything involving a radical, you can only take even roots of positive things, square roots, cube roots, etc., where you can do odd roots of anything. Then these are your basic properties of limits. You saw a couple homework problems last night that asked you to apply these. And again, because this is a different book, some of the notation might look different, but I tried my best to find things that were comparable. All this is saying is that if you have two different functions, in this case f and g, with two different limits, let's say L and K, if you're being asked to find a limit that has some scalar multiplication, just multiply the scalar times the limit. For sums, differences, products, quotients, you can simply perform the indicated operation. And same for the power rule, just take whatever the limit is and raise it to the appropriate power. Finally, if you are trying to find the limit of a polynomial or a rational function, a polynomial means you'll have multiple terms. A rational function means you'll have a numerator with x's and a denominator with x's. Again, so long as the function is defined wherever you're trying to find that limit, then direct substitution is always your first attempt, and that's when life is good. So let's go ahead and just remind ourselves what those questions would look like. So here in example 1, find the limit using direct substitution. And again, some of the methods that we talked about yesterday were finding the limits from a graph and finding the limits from a table. Certainly finding the limits from a table is kind of the most cumbersome, takes the most time, and really it's a very inefficient approach. Finding a limit from a graph is great if you have the graph in front of you, but it's also a little bit tricky from the graphing calculator, since if the values are very, very small, it's kind of difficult to see what's going on there. So an algebraic calculation of a limit, which today's lesson is all about, is really kind of the most direct and easiest approach, so long as it worked. So if you are trying to find the limit as x goes to 5 of this polynomial, all you're going to try to do is see if you can plug this functional value in for all of the x's and then calculate it. Now, this is kind of some extra step, just kind of applying the rules for you, showing that if you're finding the limit of different terms being added or subtracted, you can just break those limits up. This is an example of using a scalar multiplication rule, but chances are you're going to jump right to here. Everywhere there's an x, you're going to plug a 5, you're going to perform the operations, and you're going to get a limit of 39. Again, so long as you're able to calculate a number, you can feel confident that that is in fact the limit. Another one here in example 2, again, this is a rational function because there's variables in the top and bottom. But again, all you want to do is, fingers crossed, hope that everywhere there's an x, you can put a -2 in, and then cross your fingers that you're going to get some example. Again, these right here are just kind of showing you the application of the limit rules. You do not have to show me that in your work unless you would like to. Chances are you're going to jump right to here. Everywhere there's an x, put a -2. Very carefully calculate, and you will in fact get the limit is equal to -1/11. So that begs the question, are all these problems going to be this easy? Unfortunately not. So what if direct substitution cannot immediately be used? And notice I say the word immediately because it means that you're not able to use direct substitution in the first step. If that happens, then you must employ some algebraic technique. Please note that these are also called analytical techniques. Those two words are equivalent. And you basically have to simplify or rewrite the function into some other form so that you can simply plug the value in and use direct substitution. How will you know for sure that you need to do some operation? How will you know that direct substitution does not work? Well, you're going to get something called the indeterminate form. And the indeterminate form are the values for which a limit cannot be determined. These are all the different indeterminate forms that you're going to see in your mathematical career. We're going to focus mostly on this first one, 0/0. If you try to use direct substitution and in the first try, you get 0/0, that is called the indeterminate form, which means that the limit cannot be determined. It doesn't necessarily mean game over. It just means that you have to do some other technique. So the first technique is using factoring and dividing out. Unfortunately, it doesn't kind of have a cooler name. So here's the problem in question, the limit as x goes to 1 of x minus 1 over x squared minus 1. So again, using what I mentioned, that direct substitution is your first line of attack, you would try to plug a 1 in for all the x's. If you were to do that, you would get 1 minus 1 over 1 minus 1, which of course would be 0/0. Again, please make sure you know that is called the indeterminate form, which means I cannot determine a limit yet. What I'm going to do is I'm going to realize that my denominator, x squared minus 1, that's our very good friend, the difference of squares. And you're then going to factor the bottom as x plus 1, x minus 1. Why is that good news? Well, you can, of course, reduce those x minus 1s. Then, once you're left to the reduced form, the limit as x goes to 1 of 1 over x plus 1. Now, when you do direct substitution, you get a nice, wonderful, beautiful answer of simply 1/2. When you're doing this work, some people kind of get a little bit lazy and drop the limit statement in every line of work. If you do that, it's not that big of a deal, but I would try to recommend you strongly have it in the first step of work and also the last step of work. You'd be surprised in my calculus classes how often people stop at this step because they forget to actually take the limit. So of course, try not to do that. Let's go ahead and do one together here. And again, if you're feeling like a tough guy, or if you just love factoring, I mean, who doesn't? You could go ahead and pause and try it. Otherwise, let's take a look here. Your first order of business, again, would be to try to plug a 2 in for all the x's, but unfortunately, that's going to yield 0/0, which we know is the indeterminate form, which means that's a no-go. The top is clearly as simple as it can be. The bottom, because there are 4 terms, that, of course, is going to be factor by grouping. To factor by grouping, take the GCF out of the first 2, which would, of course, be x squared. Take the GCF out of the second 2, which would be a positive 2. And again, hopefully you remember the fact that you're getting that repeat. That's how you know that you're in good shape. So x minus 2 in the numerator, x squared plus 2 times x minus 2 in the denominator. Again, miracle of miracles, look at that. Those x minus 2's cancel. And spoiler alert, that should happen a lot. If the whole point of tonight's homework is to use some kind of algebraic technique, if that technique does not make the problem into something you can solve, chances are you're not doing it right. In this next step, again, this is where I recommend you don't forget the limit statement, because if you don't write the limit statement, you might forget to actually calculate it. On the numerator, you have canceled everything out. So of course, that's not a 0, but it's a 1. Another really important thing to watch out for. So now that you're down to this simplified version, everywhere there's an x, put a 2. That is going to give you 1/2 squared plus 2, which is going to give you a final answer of positive 1/6. You're going to see a lot of fraction action in these problems. And again, no worries, but the fraction I think is clearly preferable to the decimal. Remember that if you were to see 4 terms like this and you could not do grouping, you'd have to do your old friend, the rational root theorem. Remember, the rational root theorem is where you make a list of p's and a list of q's, and then you'd have to do synthetic division until you find factors that work. I don't think you're going to see any of that this chapter, but never a bad idea to remember it. One of the factoring techniques that you definitely are going to have to remember is the sum and difference of cubes. You'd be surprised how often this is a limit killer for people because they just forget that it exists. So the sum of cubes, a cubed plus b cubed, and the difference of cubes, a cubed minus b cubed. Remember, of course, SOAP. You're going to have the same sign to start, the opposite sign, and then always positive. And then a and b is whatever you have to cube to get the first term and whatever you have to cube to get the second term. So here's an example on the left-hand side of one using the sum of cubes. And here's an example over here using the difference of cubes. And of course, notice in the second example, your a and b are more than just a single number, and that's perfectly fine. So don't forget that the sum and difference of cubes is a thing, along with all your other factoring strategies, greatest common factor, AC method, difference of squares, rational root theorem as a last resort. So the better you are at factoring, I think the easier you're going to find this lesson. So after you've tried direct substitution and after you've tried factoring and canceling, your next option is the technique called rationalizing. Now, here's the thing. You guys have been rationalizing denominators for a while, but when it comes to limits and calculus, you almost always are asked to rationalize the numerator. So take a look at the problem here. The limit as t goes to 0 of the square root of t squared plus 9 minus 3 all over t squared. Now, just a little reminder here, the square root of t squared plus 9, that is not t plus 3. It is not t minus 3. It is not something that you know, so please don't pretend that you do. Again, if you tried direct substitution, you would unfortunately get 0/0, which means that is not going to work. Because there is no factoring to do, and because there is a square root, that is your clue that you are going to try to rationalize the numerator. So if you take a look at the numerator, what you're going to do is just like you did back in the day when you rationalized the denominators, you're going to multiply by the conjugate. Remember that the conjugate means the same front, the same back, but then the opposite middle. So whenever you are rationalizing the numerator, you're going to multiply by the conjugate. Of course, you have to do it on the top and you have to do it on the bottom. Now, first take a look at the bottom. If you multiply t squared times the square root of t squared plus 9 plus 3, there is nothing nice and easy about that multiplication. So notice that I have just left it as the two values times each other for the whole way through. So again, your denominator, you're almost never going to multiply. You're just going to leave it as one messy thing times another. But the whole point of doing a pair of conjugates is, remember, normally when you multiply binomials, you have to do a FOIL. But the nice thing about a conjugate is you always cancel out the outers and the inners. So you really only have to do first and last. So if you do the first, the square root of something times itself, the square roots just cancel, and notice that that's where I get the t squared plus 9. Then if I go to do the last, that's a negative 3 times a positive 3, which gives me a negative 9. Notice that the positive 9 and the negative 9 cancel, and all I'm left with on the top is a t squared. Notice that the t squared from the numerator and the t squared from the denominator, well, those are now allowed to cancel, which brings me down to this value right here. Once I have simplified, reduced, and canceled, I usually will be left with something that I now can plug in for. And if I go ahead and plug a 0 in for all the t's, I'm going to get the square root of 9, which is 3, plus 3, which gives me a final answer of 1 over 6. So again, this is, I guess, technically the third technique, which is rationalizing the numerator. Let's go ahead and try another one all the way through. So take a look at this problem. Again, you should verify that if you plugged in 0, you would get 0 over 0. So that means I'm going to have to go ahead and multiply. So looking at the top, remind myself that this is in a parentheses. I'm going to multiply by the conjugate, which is the square root of x plus 2 plus the square root of 2. And I have to do one of those on the top, and I have to do one of those on the bottom. Put a little more parentheses here to keep it nice. So then this is the limit as x goes to 0. And again, on the bottom, you pretty much always wind up with what looks like a big old mess, although it will always simplify in the end. So now I'm going to multiply the first times the first. So if you multiply the square root of something times itself, you're just going to get x plus 2. Then if you multiply the last times the last, a negative times a positive is a negative. A radical 2 times a radical 2 is a regular 2. Notice that the 2 and the negative 2 cancel. Notice that this x and this x will then cancel. So this is the limit as x goes to 0. Because everything canceled off the top, there's still technically a 1 there. So square root of x plus 2 plus the square root of 2. You're now allowed to hopefully plug in that 0. So if you do so, the limit statement goes away once you actually plug it in. You're going to get 1 over the square root of 2 plus the square root of 2. Hopefully you remember that square root of 2 plus the square root of 2 is 2 square root of 2. Even though you are rationalizing the numerator, you still don't want to leave your final answer with a radical in the denominator. Rationalizing the numerator is really more a matter of finding a limit. So I'm going to multiply top and bottom by the square root of 2, which is going to give me a final answer of the square root of 2 over 4. That is the answer that I'm looking for, and that is, in fact, the limit. So again, the more you do of these, it gets quicker and easier, dare I say it, even fun. So this would be a good time for you to pause and try it. So here, for example 7, go ahead and see if you can find the limit using this technique. All right, so if you tried it, your final answer should have been that the limit is equal to 1/8. If you go ahead and multiply top and bottom by the conjugate, you just have to be a little bit careful. When you multiply the pair of conjugates, you have to do 16 minus that entire quantity, 18 minus x. If you forget to distribute that minus, you're not going to get the cancellation of the x minus 2's. Once you do get that cancellation, all you're left with on top is a 1. On the bottom, if you plug in 2, you're going to get 4 plus 4, which is giving you a final answer of 1/8. The final technique for today has to do with simplifying complex fractions. Now, there are a couple different ways that you might have learned how to simplify complex fractions. I'm going to show you my way, which is to find common denominators in the top and bottom and then multiply by the reciprocal. The other technique is to multiply everything by the LCD. So if that means something to you, if you understand that terminology, feel free to do it however you learned it to simplify complex fractions. Otherwise, here's my suggestion. So again, you're trying to find the limit as x goes to 3. Unfortunately, if you plug in that 3, you're going to get a 0 over 0. Just a quick reminder, now that we're learning the harder techniques, don't forget about the direct substitution for easy things. There will be a bunch of problems, on the quiz or just in future assignments where you can just plug the number in. So don't forget to try that first. So from here, again, this is what we call a complex fraction because you have fractions in the top and you have fractions in the bottom. So my advice when you're trying to do these is you're going to first, there's your big fraction bar. You're going to find a common denominator in the top, a common denominator in the bottom, and then eventually you're going to multiply by the reciprocal. First, take a look at the denominator. Technically, x minus 3 over 1, that is already in a common denominator, so that's good to go. If you take a look at the numerator, you have a 3 and you have an x. So that means that your common denominator would be a 3x. What do you have to multiply this x by to get 3x? You'd have to multiply by 3 over 3. So you're going to get a 3 here. Minus, you would have to multiply by x over x. So you're going to get an x here. Once you have found a common denominator in the top and in the bottom, you're going to go ahead and multiply by the reciprocal. So the limit as x goes to 3, multiplying by the reciprocal, also known as keep, change, flip, or keep, change, however you learned it. You're going to keep the top fraction, change the big division bar to a multiplication, and then you're going to flip the bottom fraction. So anything that is part of a binomial has to stay together. And then you're going to try to cancel. So 3 minus x and x minus 3. Obviously, those are not a pair of exact opposites. If they were, or a pair of exactly the same, if they were, you would just cancel them to make a 1. Because they are exact opposites, hopefully you remember that exact opposites reduce to be negative 1. So I can cancel out these two things, but I'm left with a negative 1. And you generally put that negative 1 in the numerator. So the limit as x goes to 3 of negative 1 over 3x, you can now safely go ahead and plug in that 3, which is going to give you negative 1/9 as your final answer. So again, will things always cancel out nicely? Yeah, that's kind of the whole point. Just like the previous problems where you were rationalizing, if things don't cancel, it's not going to work, and they're designed to work. So if they don't, a little bit of mistake there that you want to be mindful of. Again, just a quick reminder over here in case you have a question about what I did there. X minus 3 over x minus 3 compared to x minus 3 over 3 minus x. In the first instance, they are exactly the same, which means they cancel out completely to be a positive 1, whereas in the second instance, they are exact opposites. And again, the opposite of a positive x has to be a negative x. The opposite of a negative 3 has to be a positive 3. Those would cancel out to be a negative 1. And then don't get it twisted with mystery option number 3, which is what if you had x minus 3 over x plus 3? Those are not a pair of exact opposites. They are not exactly the same either, which means the problem is over. No cancellations are allowed. So again, these are the 3 kind of things that you want to be on the lookout for. Final problem of the day here. So again, you're trying to find the limit by using the complex fraction. So again, if you try to plug negative 2 in, sadly, you are going to get the indeterminate form. So you're going to have to go ahead and find some common denominators. There's my big old fraction bar. And again, the denominator is good to go. If I look at the numerator, I have a 2 and I have an x plus 4. So I'm going to make my common denominator 1 of each. In order for that to work, I have to multiply the top fraction by 2 over 2. In order for that to work, I have to multiply the second fraction by x plus 4 over x minus 4. Pay close attention to this subtraction because you technically have to subtract the entire quantity. If you don't, there's going to be trouble. And then who knows? And again, notice that I kind of drop my limit statement every so often. Technically, you could simplify and then just plug it back in the final step. That's going to kind of be up to you. I'm going to keep, change, flip, and simplify at the same time. So if I look at my 2 minus x plus 4, this is going to be 2 minus x minus 2. So 2 minus x minus 4. So when I go to do my keep, change, flip, if I simplify that, that is going to be negative x minus 2. So negative x minus 2 over 2 times x plus 4. That is my numerator or my keep. Change the big multiplication to a division and then go ahead and flip. Again, make sure that you remember anybody who is part of a binomial has to stay together. You again have an example where you have a pair of exact opposites. So the opposite of a negative is a positive in both of those instances. So again, you are allowed to cancel them, but you have to be left with a negative 1. So you're going to find the limit as x goes to negative 2. Again, we generally put that negative 1 in the numerator of 2 times x plus 4. You are now safe to substitute in. That's going to give you a negative 1 over a 2 times 2, which is going to ultimately give you a final answer limit of negative 1/4. So again, while there are, a lot of algebra techniques going on here, they should be getting easier. They should be getting muscle memory. Again, dare I say it, a little bit fun. So you're going to have plenty of these to try in tonight's homework. So thanks very much for tuning in, guys, and we will catch you next time.